Have you ever wondered what the instruction manual for life itself actually looks like? Well, today, we're going to open it up. We are going to decode the secret language that builds literally everything, from the simplest plastics to the most complex medicines. This isn't just a chemistry lesson. It's the story of how molecules are made. And you know what? It all starts with one superstar element.
Right, think about it like this. Imagine a gigantic Lego set, but with only one type of superstar piece. Just one. A piece that can build pretty much anything you can dream of. That's the core idea we're diving into. We're going to see how a single element, with just a few simple rules, creates the mind-boggling diversity of life all around us.
So, what is this field we're talking about? It's called organic chemistry, and it's not some dusty, abstract topic. No way. It is the study of life itself. It's the chemistry of us, of our bodies, and of every living thing we know. And the main character in this whole story? The element carbon. And here is carbon's unique superpower. It's a fancy word, catenation, but all it means is that carbon is amazing at linking up with other carbon atoms. It can form these long, stable chains, create these intricate rings. It can even form double or triple bonds with itself. This ability makes it the ultimate molecular building block. Okay, so every great structure, right, it starts with a blueprint. Some kind of basic framework. Well, in organic chemistry, that framework is called the carbon skeleton. Let's take a look at the two main designs you'll see.
So you've basically got two big families. First, you have your aliphatic and alicyclic skeletons. Think of these as the fundamental scaffolds, straight lines of carbon, branched out structures, and just some simple rings. But then you have aromatic structures. Their big claim to fame is a super stable flat ring called a benzene ring, and believe me, that special ring unlocks a whole different world of chemical properties.
All right, so we've got our basic skeletons. But a skeleton is just a frame, isn't it? To give a molecule its purpose, its unique personality, we need to start adding the special pieces.
And these special pieces? They're called functional groups. A functional group is the part of the molecule that gets things done. It's the active site, the piece that decides how the molecule is going to behave, how it will react, and what its job is. It's what makes an alcohol, or what makes an acid. It's the whole personality of the molecule.
Now here's just a quick peek into the huge catalog of these special pieces. And hey, don't worry about memorizing this. Seriously, just get a feel for the variety. You've got alkenes with their carbon-carbon double bonds, alcohols with that little OH group, carboxylic acids. Each one gives the molecule a totally distinct identity and a different set of chemical tools to work with.
Now, you might be thinking this catalog is totally chaotic, but there's actually a beautiful order to it. See, molecules with the same functional group all belong to the same family, what chemists call a homologous series. It's kind of like a line of car models. They all have the same type of engine, but some might be a little longer or shorter than others.
With millions, literally millions of possible molecules, how on earth do chemists keep track of them all? Well, they developed a universal language, a super precise instruction manual for naming every single one. Let's see how that language works.
And the system is beautifully logical. Every single name has three parts. First, the stem tells you how long the main carbon chain is. Then, the suffix identifies the most important special piece, that main functional group, and finally, the prefix tells you about any other attachments and exactly where they're located.
Let's just focus on the stem for a second. This is the easy part. It's just a code for the number of carbons in the main backbone. 1 carbon is meth, 2 is eth, 6 is hex, and so on. It's really just a simple counting system.
So, let's try to decode 1. 4-ethyl 2-methylheptane. Looks complicated, but it's not. We start at the end. The stem, hept, tells us there's a 7-carbon chain. The suffix ane tells us it only has single bonds, and the prefixes tell us there's an ethyl group hanging off carbon number 4 and a methyl group on carbon number 2. See? It's a perfect set of instructions.
Okay, now for one of the most mind-bending and powerful ideas in all of chemistry. What happens when you have the exact same set of Lego pieces, but you snap them together in a different way?
This brings us to the world of isomers. These are molecules with the exact same parts list, the same formula, but a different structure. And that structural difference, well, it changes everything. It can be the difference between a sweet smell and a rotten one, or even the difference between a life-saving medicine and a poison.
There are two main flavors of isomers. Constitutional isomers are pretty easy to spot. The atoms are literally wired together in a different order. But stereoisomers, they're much more subtle. The connections are identical, but their arrangement in 3D space is different. That 3D shape is where things get really, really interesting. One cool type of stereoisomer is called a cis-trans isomer. The key here is a carbon-carbon double bond. A single bond can rotate freely, like an axle. But a double bond is rigid, like a plank of wood. It can't rotate. Because it's rigid, the groups attached to it are locked in place, either on the same side, which we call cis, or on opposite sides, which we call trans. Same parts, two totally different shapes.
Now for an even more subtle kind of 3D difference. And to get our heads around it, let's look at where the word for it comes from. The word is chiral, and it comes from the ancient Greek word for hand.
Think about your hands for a second. They're mirror images of each other, right? But you can't perfectly stack one on top of the other. Your thumbs will be pointing in different directions. They're non-superimposable. Well, molecules can be the exact same way. These molecular left and right hands are called enantiomers. They are perfect mirror images that are fundamentally different in 3D space.
So, what's the magic requirement for a molecule to have this handedness? Well, the molecule needs a special carbon atom called a chiral carbon, and the key is the number 4. A chirocarbon is a carbon atom that is bonded to 4 completely different things. If even 2 of those groups are the same, the molecule has symmetry, and it becomes superimposable on its mirror image, kind of like a plain coffee mug.
So let's just step back for a second and think about this journey. We started with just a single atom, carbon, and its incredible ability to form skeletons of chains and rings. Then we learned the rules for adding all these special pieces.
And from that really simple starting point, we've unlocked a language that describes the skeletons, the functions, the names, and even the super subtle 3D shapes of the molecules that build our entire world.
And why does any of this matter? Well, take amoxicillin, a really common antibiotic. This life-saving molecule has 4 chiral carbons, 4 sensors of handedness. Its very specific 3D shape acts like a key, one that's designed to fit perfectly into the locks of bacterial cells and stop them from growing. If you used its mirror image, its enantiomer, the key wouldn't fit, and the medicine would be completely useless.
So the next time you look at a medicine or a food ingredient, or even your own hand, you'll know the secret. It's not magic, it's a language. A language of building blocks, special pieces, and 3D shapes. And it's a language that, now that you know the basics, lets you read the instruction manual for life itself.